So hi, I'm heading out to surgery tomorrow. It's not a big deal, but probably be off of YouTube for a little while. So maybe make a wrap it up video here, and I'll be fine. I'm just gonna be out for a couple days. So if you do want to make a responses video, that's fine, and you've got plenty of time to think it over and mull it over or whatnot, or any of my videos. I'm certainly happy to. I'll be back at YouTube. And I won't be able to help out with Hangout. I guess Penrose also going off doing his own thing. So we'll both be indisposed this weekend. So I won't be able to get it together. But I'll be back some point. This video here is heading out to Hythloday. And first going to give out a shout out to the Logic Only Zone. Now, Logic Only Zone, he's put together this new program. It's called the Real Logic Only Zone. And I think he's really trying to get into, how it is to be real. How to be a real person in the real world. I think it seems like a pretty cool story. He's shooting videos on his bed and on his toilet. Just kind of, chatting and being a person. And I dig it. I dig it a lot. I think it's a great show. And in the last episode, he's talking about me and what I've been doing. And he's figuring things out, using some reasoning, to work on the problems. And he's like, he notices that I'm breathing funny as part of something is weird right now. He says it's because I'm in love with him. And it's not. It's because I'm in love with your bathrobe, your red bathrobe. So you're being real. I'm going to come clean with you here, right? So the video I posted before I started messing with Logic Only Zone, like if you go to the first Logic Only Zone video on my camera and on my channel, and look at that one. The video before that is this one called The Unpleasant Punisher, where I lay out a scientific theory called The Unpleasant Punisher. And this wasn't maybe so much about logic as science, and I wanted to kind of test out my social theory on YouTube by adapting the role of the Unpleasant Punisher and seeing what reactions might be. So I decided to be a kind of a Lex Luthor type, and come at the guy in the red bathrobe. So I learned a lot from it all, and I think it was worth doing. I learned some stuff about escalation, because then it became a larger conversation about logic and whatnot with a whole bunch of people. So that was really fun, and I'm kind of thinking of this. This is kind of maybe the end of it all. So, Mr. Zone, this is for you there, buddy. There you are in your red bathrobe, heading out to do your thing. All right, man. Oh yeah, Hythloday, sweet. Okay, so Hythloday wants to. He picked Penrose tiles because he has got awesome taste in math. Like, look at this badassness right here, right? So this is kind of a similar kind of diagram to what Hythloday was showing. It's as similar as I could find. I'm coloring it in, showing these rings. So here's the exact center of the Penrose tiles. And at the center, it has, this symmetry. If you draw a line down the middle of it, then it'll be completely symmetric. But we'll get into symmetry a bit later. What Hythloday is talking about is translational symmetry, which is different. But this is the center of the tiles. This isn't going to give it justice. This I can talk about the rings a little bit, and how as the rings go out, the rules change. There's a rule for how the rules change, and so that each ring will be its own thing as it goes out and out and out from the center. These things are pretty hip, but to really give it what it deserves, we're going to look at the old TV here. So this here is a YouTube video of a phone app called Penrose, and Penrose has Penrose tiles that you can have this whole Penrose, the actual thing, in your phone. And so he just started the app, and so this here is the center of it, and this is the center, and it's coming out in the rings from there, right? He's got it colored in a little bit different than I do, but that's the Penrose right there. It's a fun app. So let's just go ahead and start it. Okay, so now, yeah, he's got it as background, but then now we can see how it's just a huge plane. This keeps going on and on and on, and it never really repeats. There's local repetition, just like the digits 314 will appear again in the digits of pi, but the larger it goes out, it doesn't repeat, and it gets pretty big. It just goes on forever without repeating. Yeah, it's pretty slick. So that's just to give you an idea of what the thing looks like. Okay. So back to the lecture. Okay, so here we have some Penrose tiles. We're talking about this is the center of it, and the rings come out from there. Now, I guess we'll just come back to that. Okay, good. Look, here's the thing about translational symmetry, right? So there's localized areas of translational symmetry, right? So like this star can be put on this star, and this star can be put on this star, but as it gets, like, from there, there'll be some problems in the overall maze if we did that, right? There'd be, one would have a line where one didn't have a line. This kind of stuff. So, because it like, the bigger shape here, like this whole bigger shape here, this whole thing will repeat many times in the actual thing, but it'll be such a way that the things around it are different, or somewhere in the whole big space. If you put one space on top of this space, then there'll be some different deal going on. So the whole thing's made out of these two shapes. And the angles on these shapes relate to a pentagram, like 360 over 5. And this kind of relates to a star. We'll see how this... The thing with the pentagon is that it can't tile a plane by itself, right? What we just saw on the television was a whole plane. It was being tiled by these tiles, and they just would go on forever. Now, if we did that, let's say with squares, it would just be a grid, right? And it would just go on forever. Squares are easy. And the same with like equilateral triangles, right, which are 3. And shake on the other way. So equilateral triangles can tile a plane, but pentagons can't, right? Triangles are 3, they can do it. Squares are 4, they can do it. But then when we get to 5, that's when it looks like this. There's a pentagon tiling. See, when you try and put the pentagons together, there's these weird holes, right? And that's what lets Roger Penrose kind of do the thing, sort of. Right, this has some translational symmetry, like we can put this shape on this shape, and it wouldn't screw up this, mapping. This is like a grid, like it doesn't do anything that changes. If we put these red ones on the pink ones, then it would still, everything would still match up on this one. So I want to save that for next. I'm going to do that right. Okay. So yeah. So these are the shapes that we see in the Penrose tiles. but they haven't been arranged in any kind of special way. They've been arranged in a kind of a symmetrical way, such that we can have translational symmetry. All kinds of, anywhere we put this, it'll have translational symmetry. So it's about the rules that he does to, create this, right? That it starts like this, and there's a rule that if it does this, and it does this, and there's some mathematical algorithm that he uses to do this, and that mathematical algorithm is based off of phi, the golden ratio. So here's a pentagram, and we're going to assume it's an equilateral pentagram. I didn't draw it perfectly at all, but here's our perfect pentagon in the middle, and we've labeled some points. And what we're saying is FG over BC equals phi. So FG over BC is phi, is the irrational number that has this phi-ness to it, and then to use that number so that to have this come out of it is what Roger Penrose does to create this, and it's cool. It's able to explain like how crystals grow and that kind of stuff. You can do things where you can twist these things or draw lines through them such that you can make other crazy deals out of this guy. So that's kind of how the Penrose tiles works and what they are. To me, it's a way of thinking about irrational numbers, thinking about patternless patterns, repetition, non-repeating repetition. So, I mean, this is how the number pi and phi and things like that kind of work to me, is how I see them. It's like it's always the same rule, but as the same rule goes out and out and out, it just gets more and more complex. Oh, excuse me. Okay, so it's going to be about this thing called phi, and here's the Venn diagram that Hythloday asked me for. And so this green one are things that have repetition, and then this one is things that do not have repetition, and what I'm saying is phi is in both of these sets. I'm going to use induction for this one, and use deduction for this one, and two different definitions of phi. I'll use one definition for the induction proof and one definition for the deduction proof. So here's our definitions of phi. The first one is how phi is the golden ratio. It appears in the hands where like this plus this length, right, equals the whole finger, and then like this part plus this part equals the hand, or the next, I guess the fist. It shows up. It's like how to explain it? It's like one something plus the last thing equals the next thing, right? So like 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 2 is 5, 5 plus 3 is 8, that kind of thing. And that can be expressed with this. And as you can see, it's very repetitious, that phi equals all this stuff, and it's just this repeating pattern. And these dots indicate induction, that it's just going to go on and on and on. Okay, so the second one definition is phi squared minus phi equals 1. And that still has to do with that same phenomenon, but it's a different way of writing the same. Writing this is the same as writing this. This phi is the same as this phi. So what I need to show here is non-repetition. And we will do a proof by contradiction in our video on why the law of non-contradiction doesn't apply to everything. So what we're showing is that phi squared minus phi equals 1 implies that it's not P over Q, that it can't be expressed as some kind of rational number, right, where P and Q are integers with no common factor. So first step, we'll rewrite our premise, and then we'll make our assumption, right? We're trying to get not P over Q. So we'll just go ahead and assume that phi is P over Q, because we're doing proof by contradiction. And then we'll substitute P over Q into our premise. So we get, instead of phi squared minus phi equals 1, we get P over Q squared minus P over Q equals 1, just by substituting. And so then we're going to multiply both sides by Q squared. And so it'll cancel here. We just get P squared. This Q on the bottom, if we multiply by Q squared now, it just becomes a Q on the top. And 1 times Q squared is Q squared. And then we'll factor by P, right? Because we got P here and P here. So we can factor that out. And we get P times P minus Q equals Q squared. Now, what we said in our assumptions was that P and Q are integers with no common factors. And then P would be a common factor of Q squared. Right, because this implies that P divides Q squared evenly because P is an integer. But it's the kind of thing, as N.J. Wildberger would point out, where we never used common factors from our assumption part of it. It still could have all been integers all the time. We never used that common factors part, right? And from here, I mean, we basically just discharge the assumption and say not P over Q, right? And so doing the proof by contradiction in my claim that the law of non-contradiction doesn't apply to everything reminds me why I believed contradictions existed in the first place. All right, so I guess that was probably maybe the longest joke ever on YouTube. It took maybe a couple weeks, so awesome. It's been a lot of fun, and I will see you all soon.